As 3I Atlas, an interstellar object roughly the size of Manhattan, drifted closer to our solar system, astronomers and enthusiasts alike were captivated. Initial observations labeled it as a comet, yet recent images show it appears to have lost its tail entirely. This unexpected development has prompted some scientists to propose a far more radical idea, that 3I Atlas might not be a comet at all, but rather a highly advanced alien spacecraft. The James Webb Space Telescope has once again transformed our understanding of the cosmos, capturing unprecedented data on this mysterious interstellar visitor. When Webb focused its sensitive instruments on 3I Atlas, astronomers expected a typical interstellar fragment similar to objects like Oumuamua or 2I Borisov, small chunks of ice or rock expelled from distant star systems. But the detailed infrared imagery revealed something far stranger. 3I Atlas turned out to be far larger than anticipated. What was initially thought to be a modest celestial traveler emerged as a massive body defying conventional assumptions about how such objects could survive ejection from their home systems into the vastness of interstellar space. Stay with us because the revelations that follow are astonishing. If you're drawn to the mysteries surrounding 3I Atlas and want more cosmic discoveries, hit the like button to let the universe know you're watching. Every click fuels our shared journey into the unknown. Comment below with your location. It's fascinating to see who around the world is following this with us. Ground-based telescopes, including Webb's NIRCam, reveal details previously invisible. Once seen as a faint speck, deep infrared imaging now showed a massive structure reflecting heat in unusual ways. Analyses indicated that 3I Atlas was hundreds of kilometers across, far exceeding any previously observed interstellar object. The sheer scale is astounding, as conventional astrophysics struggles to explain how such a body could be ejected intact from a parent star system into the vastness of interstellar space. Webb spectroscopy hints at a possible origin. 3I Atlas may be the leftover core of a destroyed dwarf planet, retaining an unusual combination of ices, silicates, metals, and organic compounds formed in an alien stellar environment. Measurements also detected ammonia hydrates and complex carbon molecules, indicating past internal heating or tidal forces. These findings rule out the notion that 3I Atlas is a primordial comet, instead supporting the idea that it once belonged to a geologically active world now drifting through interstellar space as a relic of its former self. Scientists note that if massive fragments like this can survive ejection from star systems, it forces a reconsideration of planetary formation models and the chaotic dynamics within young star clusters, the likely birthplace of 3I Atlas. Webb's observations also uncovered evidence of a thin crust actively spewing material through fissures, revealing a slow rotation period of several days, consistent with a monolithic, resilient structure capable of enduring billions of years in the void. 3I Atlas thus emerges as a striking example of planetary fossils wandering the galaxy, remnants of lost worlds carrying the chemical signatures of their star systems. If such massive fragments are common, they may silently deliver complex matter across star systems, influencing planetary formation, atmospheres, and potentially even seeding the building blocks of life. Webb's data suggests 3I Atlas has a dense rocky core enveloped in ice and dust, resembling icy moons like Europa or Enceladus. This hints that it might have once hosted a subsurface ocean. As 3I Atlas approaches the Sun, it exhibits sublimation activity including jets rich in polycyclic aromatic hydrocarbons and nitriles, critical precursors to amino acids. This marks the first time such compounds have been detected on an interstellar object, reigniting discussions about panspermia, the possibility that life seeds can travel between star systems via wandering planetary debris. While conditions on 3I Atlas are unlikely to sustain life, its complex organic content makes it a fascinating candidate for studying the interstellar distribution of biochemical precursors. These long-traveling fragments could act as silent carriers, delivering primordial compounds to any star system they encounter. The surface of 3I Atlas tells a violent cosmic story. Smooth, bright areas interspersed with deep cratered regions suggest a tumultuous history of collisions and resurfacing, possibly from a dense asteroid belt or repeated impacts from smaller bodies. Webb's infrared images reveal a world battered by cosmic violence before its ejection into interstellar space. Spectroscopy also detected crystalline ice formed only after cycles of heating and cooling, further suggesting that 3I Atlas once experienced substantial temperatures either internally or while orbiting its host star. This supports the theory that the object belonged to a dynamic planetary system, possibly containing liquid water at some point. The immense size of 3I Atlas raises questions about how many similar bodies drift unseen among the stars, moving slowly and reflecting minimal light. Its discovery hints that interstellar space is far from empty. It may be filled with ancient planetary debris, remnants of long-lost worlds from countless stellar generations. Researchers are increasingly classifying objects like 3I Atlas as wandering relics, structurally intact fragments carrying the chemical signatures of extinct planetary systems.
Each 3I Atlas that drifts through interstellar space acts like a cosmic sample mission, bringing material from distant regions of the Milky Way without humans ever leaving the solar system. What's particularly striking is the tremendous energy required to eject an object of this size from its parent star system. Models suggest that interactions with a single gas giant would not be enough. Instead, a binary star system could provide a gravitational kick powerful enough to disrupt the orbital structure and propel the object into interstellar space, consistent with 3I Atlas's unusually high velocity. Webb's ultra-high-resolution instruments also detected faint streams of dust escaping from the object's surface. Spectroscopic analysis revealed isotopic ratios unlike anything in the solar system, reflecting origins from a star with higher metal content and distinct oxygen-to-carbon ratios. In this sense, 3I Atlas acts as a chemical messenger, carrying information from a completely different region of our galaxy. Future studies of similar interstellar visitors may one day allow scientists to map the Milky Way's chemical composition in unprecedented detail. The discovery underscores the extraordinary power of the James Webb Space Telescope. Although primarily designed to probe the earliest epochs of the universe, Webb demonstrates its ability to reveal hidden wonders in our own cosmic neighborhood, uncovering mysterious objects like 3I Atlas that had previously gone unnoticed. What once appeared as a faint speck of light is now recognized as one of the most remarkable interstellar discoveries of the decade, providing vivid insight into the chaos, evolution, and chemical diversity of planetary systems on a galactic scale. The fascination with 3I Atlas lies in its resilience. A body capable of surviving millions of years in the harsh conditions of interstellar space, bombarded by cosmic radiation and exposed to extreme cold, demonstrates that planetary matter can persist long after its parent star fades. This finding challenges assumptions that ejected planetary debris would simply disintegrate into dust. Instead, sizable fragments can survive to participate in the formation of new worlds. Webb's data provides rare observations of how interstellar matter responds to sunlight, including sublimation rates, color changes, and shifts in reflectance as 3I Atlas rotates. These dynamic processes make it a living laboratory, allowing direct study of the chemical evolution of planetary remnants from distant star systems. Beyond scientific data, 3I Atlas holds profound philosophical significance. It acts as a bridge between star systems, a reminder that planetary boundaries are permeable and that matter, and perhaps even the precursors to life, travels freely across the galaxy. Each celestial fragment tells a story older than Earth itself, carrying traces of vanished worlds. Webb's measurements of 3I Atlas's size and composition highlight the importance of next-generation observatories. Future telescopes will be critical for tracking such rare interstellar visitors, performing detailed compositional analysis, and potentially even sending probes to intercept them. Recent observations reveal a surprisingly complex surface on 3I Atlas. Iron-rich silicate deposits lie alongside frozen methane and reflective layers of crystalline ice, pointing to a geologically active past that may have included tectonic activity or cryovolcanism before its ejection from its home system. This suggests that planetary geology across the galaxy may be far more diverse than previously assumed. For cosmochemists, 3I Atlas is a treasure trove. Isotopic anomalies provide new insight into how stars synthesize and distribute elements throughout the galaxy. Each signature acts as a timestamp from a distant stellar nursery, offering a chemical history far older than Earth. Its existence also underscores the limits of human observation. Massive, hundreds of kilometer wide bodies drift unseen until they approach our solar system. Webb's data indicates that 3I Atlas retains heat unusually well, releasing energy slowly and unevenly, suggesting a dense interior with a rockier metallic core enveloped in ice. Minerals detected in its spectra indicate conditions that require liquid water or high temperatures, hinting at potential hydrothermal activity beneath the icy surface. A key question remains: how has 3I Atlas survived intact for millions of years in the vacuum of space? Its protective crust may hold the answer. Cosmic rays cause the ice to sublimate and refreeze continuously, creating a self-repairing shield that preserves its internal chemical structure. In this way, 3I Atlas becomes a nearly perfect archive of the history of worlds that once existed outside our solar system, a lonely time capsule, pristine and ancient. As 3I Atlas approaches the outer planets, subtle orbital shifts reveal that its mass is far greater than surface brightness alone would suggest, confirming it is both massive and unusually dense. This demonstrates that 3I Atlas is not a fragile comet, but a substantial fragment of a giant planetary body. Its composition of rock, metal, and ice resembles that of icy moons like Ganymede or Titan, as if a potential planet had been torn away from its system before fully forming. Confirming such an object would require updating traditional planetary formation models. Previous simulations suggested that bodies larger than a few tens of kilometers could only survive ejection under exceptional circumstances. Yet 3I Atlas is hundreds of kilometers across, likely expelled by a chaotic event in a dense stellar nursery. Close encounters within such clusters could disrupt entire planetary systems, sending nascent planets and protoplanets into interstellar exile. In this scenario, 3I Atlas may be the survivor of a cosmic catastrophe, its surface bearing the marks of violent events from long ago. Webb's continued observations uncovered even more secrets. The object's light curve shifts periodically, revealing the rugged terrain of peaks, basins, and deep fissures. Infrared imaging captured sunlight glinting off sheer ice cliffs as 3I Atlas rotates slowly, showing features frozen in time. Cracks formed by tidal forces or ancient collisions now stand motionless, creating a geological record preserved across millions of years of interstellar travel. Each rotation of 3I Atlas is like a map of a long-past catastrophe, a panorama of alien landscapes maintained perfectly over eons. These features also suggest that interstellar objects can play a role in young planetary systems. If an object like 3I Atlas were to pass through a protoplanetary disk, it could contribute heavy elements and complex molecules, potentially aiding planet formation. This raises questions about the transfer of chemical or even biological materials across star systems, connecting the galaxy in unexpected ways. As telescope data accumulated, astronomers began creating detailed models of 3I Atlas's origin. One scenario envisions a young planetary system dominated by a gas giant, disrupted by nearby stellar encounters. Moons and small protoplanets were scattered, and one object roughly the size of a small moon was hurled into interstellar space, eventually drifting for millions of years until chance brought it into the solar system. Its arrival was both coincidental and inevitable, a convergence of cosmic orbits governed by gravity. 3I Atlas has renewed interest in identifying similar objects. If Webb can gather detailed spectra from this distant visitor, next-generation telescopes may map populations of rogue interstellar bodies. Some could be temporarily captured by star systems, alter their paths, or even collide with planets, reshaping our understanding of cosmic interactions and planetary safety. Its chemical diversity is particularly striking. Webb spectroscopy detected not only ices but metals like nickel and iron, indicating that 3I Atlas originates from a body that underwent a complete planetary cycle: formation,
melting, differentiation, and eventual destruction. The outer layer contains clathrate hydrates, crystals that trap gases and release them as they sublimate, explaining the intermittent water jets observed by Webb. Internal pressure remains significant even after millions of years, showing that 3I Atlas is not inert but a chemically active remnant. These findings contribute to a broader scientific goal: understanding planetary diversity. While exoplanets provide theoretical models, interstellar objects like 3I Atlas offer tangible, traveling specimens from other star systems. Its large size hints at the possible existence of many more rogue planets, icy worlds, gas giant cores, or even full planets wandering the galaxy undetected. 3I Atlas may be only the first of countless such discoveries. Thermal maps from Webb reveal tiny warm spots across the surface, suggesting that slow chemical or geothermal processes persist even near absolute zero. This challenges the assumption that interstellar wanderers are entirely lifeless. Culturally and philosophically, 3I Atlas captivates the imagination. A fragment older than the Sun drifting silently through the solar system reminds humanity of the continuity of matter and time. Each atom in our bodies, each speck of dust on Earth, carries the story of the galaxy, history far older than human civilization. By capturing its faint light, Webb essentially captured a cosmic archive, frozen rock and organic material traversing the void for millions of years. The discovery also serves as a benchmark for future exploration. Plans for interceptor missions are being considered, with probes designed to rendezvous with interstellar objects and retrieve samples for laboratory analysis. Thanks to its size, 3I Atlas offers an ideal test case for designing orbital trajectories and recovery technologies, laying the groundwork for a new era of interstellar exploration.